Hello, Standoff. And the next presentation will be a continuation, next one in the series by Vyacheslav Moskvin, Hacking a Factory. So let's continue, it should be interesting. Hello, everybody again. I'm really grateful to all those who stay with us. Continue to listen to my short series called How to Hack a Factory. So let me give you my agenda for today. I will actually deliver 2 speeches today, one from 4 till 6 and the other from 7 until 8 Moscow time. And we'll talk about firmware. Previous time, we discussed how you could obtain the firmware and decrypt it. Now we will discuss how you can upload it using the right address so that, all the links are in the right places. Also, you may find the information useful on how to create the right signatures. After we are successful doing this, we will discuss what we are looking for. That is, we will discuss PLC vulnerabilities, both typical and atypical ones. And we'll try to entertain you by quoting from practice. When this is done, we will discuss networking issues, since usually we interact with the PLCs via the network. We'll need to discuss how you can find networking functions. Sometimes it's not really clear where these networking functions can be found. We'll summarize it in the end, and I will be delighted to take your questions. Without further ado, let's rock and roll. So we shall start by looking at loading the firmware into IDA. Vladimir Kononovich helped me prepare this part of the presentation, for which I'm grateful. So, we are assuming we already have the firmware. If you don't remember how we did it, you can revisit the recording from yesterday. An example illustrating the firmware from one of the devices we started in our lab is shown on the screen. It should be pretty obvious. There are no headers here. And even the format is not clear. It's not clear if it's a code or not. Well, I can tell you that it is a code. It's an executable. However, simply by looking at it, it's pretty difficult to identify the processor used, because we don't really see the typical instruction byte, which we should be able to find in ARM-based or x86-based CPUs. So how do we upload this code into IDA, and how do we start using it? Here, just like elsewhere where we analyze the firmware, Binwok can come in handy. Binwok is a utility that has been around for quite some time, and it's very good for decompression and analysis purposes. In most cases, it is applied to Linux files, and it is very good at unpacking files belonging to the associated file systems such as Jefferson. There is no guarantee, though, it will be of use in PLCs, because some PLCs indeed run on Linux, but the majority don't. The majority are run by totally different OSs. So we will need the -A flag With this flag, the Binwok utility will search for known CPU instruction sequences. Once such sequences are found, Binwok will compare it to the list of instruction sequences it knows, and this should tell us the CPU architecture. So we shall start our research into the firmware file. Obviously, the firmware has not been unpacked. It actually doesn't apply to firmware. But we were able to find the copyright string. What's the use of these copyright strings? If we Google for them, we will actually find something interesting right away. So obviously, this is the copyright string, Hitachi Ltd Hi 7700/4. If we study the search results, we will discover that hiding under this abbreviation is an operating system developed by Hitachi. It is based on the Mu Ultron specification. The same documentation will show that it supports a file system and multitasking debuggers, a configurator, and there are some sample drivers and SDKs that come as part of the bundle. But we don't have the file system firmware, right? This means that we're dealing with a slightly modified operating system here. This specification, called Mu Ultron, if I'm not mistaken, was developed by one of the Japanese research institutes. It can be compared to POSIX, and it's supported by various operating systems, but it's mostly popular in Japan. Moving on, we will see additional information about the operating system in Renesas website. Renesas claims that this product has been discontinued. If you read through the text, you will realize that this product has been designed for microcontrollers. Well, actually, they call it microcomputers, particularly belonging to Renesas H8 Super H family. Well, this is already something. This gives us a hint about the architecture of the firmware. So if we launch Binwok with the -A flag, we will see that it does discover some CPU instructions for the Super H CPU family. Also, if we use another utility which has similar functionality called CPU_rack, we will see that it also detects instruction sequences characteristic of the Super H CPU. So this is a very neat, easy way of identifying the CPU in question. It is much easier than checking all the CPUs in some other manner. Now let's load the firmware. Let's load the firmware in EduPro. Like I said, this firmware has no headers, which means that IDA will not have any hints about the CPU architecture, which means that we will need to manually indicate it. We're choosing Renesas SH3 Little Endian because Little Endian is more popular than the Big Endian. We are going to load it, and we are not going to change anything in the addresses. Even the firmware itself will be loaded to 0 address. We are going to choose SH7750 out of all the device names, because you will remember that our operating system was called 7700. And of all the numbers we have here, 7750 is the closest match. So we have uploaded it, and we use the context menu to choose transformation into executable. And you see that some things have transformed into code, some have not. So what we see is a bit of gibberish, so we may start doubting our success. If you can guess right away what's wrong with it, you can type your answer in the chat, and in the meanwhile, I will continue. A potential explanation is that we have done everything right, but maybe we need to choose a different CPU. Maybe we need the big endian, not the little endian. And if we perform the same operation and we reload the firmware, indicate the same address, and transform the data into code, that's what we're going to see. This is much more realistic. Let's discuss the code now in more detail. Indeed, this code is characteristic of Super H CPU family. It's a 32-bit processor which means it can process 32-bit values. However, the length of every instruction is only 2 bytes, or 16 bits, obviously. It is a quite popular processor for Japanese hardware. Funny fact is that Super H1 and Super H2 were used in Sega Saturns. So if you have experience with reverse engineering Sega Saturns, or just playing video games for this console, I guess you have been exposed to a very similar processor before. To simplify our engagement with a processor with unusual architecture, it's quite useful to look into the Options tab and put a tick in front of auto comments. Then every instruction will be followed with a comments field, which should make our life much easier. Particularly given that this CPU is using an assembler language with an unusual sequence of arguments. For example, we have the move-L constant and registry in address 0x0, which means that the register value will be written with the value of this constant. So they first indicate the source, and only then they indicate destination. In order for us to conveniently work with the firmware, we will need to identify the address where it's going to be loaded. Let's discuss why we're doing that. If we don't do it right, the links will malfunction. If we do it right, all the functions will be properly initialized. So you see my comment where constant 0044 is written into registry R0, and then we transfer there. This supports my hypothesis that it is in this address that a particular function resides. However, there is no crosslink there yet. Moreover, the address of this range, starting with A0, is considered invalid because our ROM segment ends with 100,000. However, if we go to address A44, which is, as you can see, the ending digits of this address link, that's what we're going to see. So registries R14 and R15 are being used at the start of the function. Then in register R3, some address is being written. Then there is a hop there. What's interesting about this processor is that when JSR and similar instructions are performed, there is a so-called delay slot. So when the JSR R3 at R3 command is received by the CPU, there will be yet another command performed before the transition to R3. And it's physically indicated after JSR. It's obviously the NOP command, something to be remembered when you analyze such CPUs. If you have analyzed MIPS-based firmware, you must have seen this before. Now note what happens at the start of the function. The manual shows that R14 register is a frame pointer, stack frame pointer. Similarly, R15 is similar to SP register and is a stack pointer. So, what we see here is analogous to what happens in many other CPUs. So the initial frame is saved in the stack. Then the return address is saved, and this is the BR register, or procedure register, I'm sorry. Then free space is created by detracting 20. So we can make a conclusion that the code in this address is the start of some function. So what we could see at first is effectively a function call. Based on that, we can make an assumption that the basis for such firmware is the NOP. I'm sorry, is 0A, many zeros after it. So we can actually check this hypothesis by rebasing the whole program uploaded in IDA. In order to do that, we need to choose a function called rebase program. Here you will need to indicate the value to which the whole program will be rebased and keep all the other settings default. So after IDA is done, rebasing the firmware image to a different value, we shall see that these function pointers are finally in their right places. So, which is easy to check. You can actually see the cross pointers, the cross links. And then auto-analysis will start, and therefore you will be able to analyze it properly and dance with it. What if we don't stop there? One of the best approaches to reverse engineering is zero reverse engineering, because this is a great way of increasing your efficiency and saving time. Open source intelligence is your best friend. Just Google it. Search for it on the vendor website. Search for it on GitHub. Actually, on the Renesas website, we should be able to find a downloadable upgrade file for this operating system in particular. And it will contain lots of source files, as well as SDKs, and obj and lib file libraries. What can we do about them? For the purposes of our analysis, we can automatically create signatures that the system will be able to recognize and use. In order to do that, we're going to use the PELF tool, which is part of the IDA Pro tool. It's PELF because the files we found in the SDK have the ELF file format. After we've created a path file using the PELF tool, we'll need to take care of collisions inside the file, if any. Collisions may arise because signatures of some functions may look the same. So we should be able to create signatures for IDE Pro. We'll put them in the catalog, in the folder. After that, we can press Shift F5 to select signatures to load. And see how they change. These signatures are extremely useful. We have ideas about how you can actually create many signatures out of these files, which will make your future analysis much better. Now, many new functions are properly identified, including the core functions. These are the ones that have the word kernel in front of them. You do it once, and next time you see a different version of the same firmware, or a firmware which uses similar runtime or similar libraries or a similar operating system, you will be able to reuse this library functions, thereby making your analysis much faster. So we have been able to load the firmware into IDE. We have been able to identify the functions. We have been largely successful in terms of preparing for our assignment. Let's do reverse engineering. Here, I'd like to point out that my colleagues, Sergey Fedonin and Vladimir Kananovich, have helped me greatly in terms of preparing this particular chapter. Before we get going, let's agree on what we're going to look for and what should be of particular interest to us. We are doing RE in order to identify vulns. And the particular vulnerabilities we're interested will be those that are exploitable over the network. Because networking vulns are the most probable vector of attack. So much is being done over the network now, and industrial networks are no exception. So we'll discuss the kind of vulnerabilities we'll be looking for, typical and not so typical ones. And we shall also touch on how you can actually find networking functions if that is not exactly obvious from the very beginning. Most firmware is usually written in C language. And I guess most real-time operating systems are written in C, although there may be inclusions in other languages. There will be some PLCs running operating systems like Linux or Windows, or it could be Windows SE or other embedded versions. In such devices, some functions can be implemented using other languages and frameworks. For example, it can be PHP instead of C there. The level of security we have seen in our analysis of various firmware would vary greatly. Some vendors tend to be more responsible in their development, while with some firmware, you will get the impression that everything was done properly and all security issues were tested, and then something changed and the project was rushed, and there are still yawning, gaping holes in the system. For a large share of IoT device and industrial software vendors, information security is still a low priority, which is a shame. Unfortunately, most manufacturers still love unsecure functions. Functions that, have long been avoided by software developers in many other industries. They have replaced them with significantly less dangerous analogs. And this is true, for example, for the infamous stir copy function, which is responsible for like half of all bugs you can find in PLC firmware. What else to note? Quite often in PLCs, lots of functions are simply undocumented. I've mentioned already that vendors love using their proprietary protocols for their own products. I guess there should be business reasons for that. So with these proprietary protocols, other software simply will not be able to talk. And quite often, the software will have some undocumented functions. Maybe these undocumented functions are used for debugging purposes. So if your PLC doesn't work, an engineer will arrive on site, or maybe a utility will be sent to an engineer remotely. And for example, this utility can be used to obtain a crash dump, which will then be analyzed in the office. Now that we've mentioned this undocumented function such as arbitrary memory read-write, you should be aware that this is a very common thing. It may sound ridiculous and horrible that without authorization, just by sending the right packet, you can get access to arbitrary memory read-write. Unfortunately, this is true. And this is what attackers will often do. I guess it's still being done because it's so convenient for the engineers. It makes their life in terms of debugging and updating firmware much easier. Now let's continue our discussion of operating memory read-write operations. This is something we always care about, something that we always look for when we analyze PLCs. Because it's a critical function. Naturally, reading can be the result of some other vulns, but in many cases, it's not a vulnerability, it's a feature, or at least this is what the engineers thought. Let's consider a specific practical case showing how we were able to find such a way in. So as we analyze this PLC and its firmware, we were able to find a table of functions, the function table you can see in the screen. So the functions were named, and you can note RQ CPU mem access function. Actually, you will see if you study it that as an input, it takes arguments that look like addresses, where a memory read or write should happen, and also a number of bytes that it will read or write. However, due to the complexity of the firmware itself, we required quite a lot of time to understand how this function could be used. We actually required a week of hard work to get there, because there were many abstraction levels and there were indirect calls, and we had to analyze both the firmware and the clients that would be using the same protocol. And those clients were developed both for Windows and Linux operating systems. In the end, we were able to craft the right network packet that would trigger this function. And get arbitrary access to the whole range in a very legit manner. Then we're faced with the objective of exploiting this vulnerability. This one is easy to use. This one is easy to exploit, and you can do this by actually rewriting the function pointers, by indicating a different address there, and making sure that this address contains what you need. In this firmware, the number of functions that had been developed by the vendor, were actually in the text section, and this text section was not available for writing. So we had to use pointers to operating system functions. And there was a risk that if we overwrite something incorrectly or if we choose the wrong function, a function that may be called at some other point in time, that may actually damage or flush the PLC. However, our analysis of the firmware showed that with every attempted access to the PLC, the firmware will start a new task. Let me remind you that in some numerous operating system processes like this, there is this entity called tasks. Since this was done on Xworks, they used a function called task spawn. As the chart here shows, task spawn would later on summon a pointer called functaskStackAlloc. And in this, this pointer actually allocates space on the in the stack for a new task. And since all tasks are usually started the first time a PLC is started, and after that it doesn't happen that much. So if we rewrite one of the pointers like this with our own content, we should be able to execute our arbitrary code without endangering the rest of the PLC functionality. Naturally, I should add here that after the payload, our code should actually return control to the original legit function so that the stack does get allocated. It's pretty easy to trigger such shell code. All it takes is, just connecting, feeding in the right payload, and then disconnecting. Let's consider another practical case. I guess this is a case that most people know, and it should have been well documented. You realize I'm going to talk about the S7 communications protocol, the one that is used for Siemens PLCs, particularly belonging to Series 7, S7300 and S7400. It has been well studied, and actually there is even a vivisector for it in Wireshark. And it enables analysis of numerous functions contained therein. So it enables analysis of numerous packets there. This PLC can be configured to use a particular password. So you will be prompted to enter your password if you want to write values to PLC or if you want to even read values from the PLC. Very often, PLCs are structured so that there is no password inside. And now, look at the packet. I am highlighting the obfuscated password there in the data line. It looks like an ASCII sequence. At the same time, if you analyze it in ASCII terms, you will realize it is not. And actually, it contains zeros and eights, which are not ASCII symbols, ASCII symbols. Note that the function returns error code of D602 in the firmware. If we look for the same code in the firmware, and it's actually a very popular trick to analyze all the error codes the system gives you. We are going to see which particular function actually processes it. So D602 is actually broken down into two values, senior one and junior one, and still it can be found. If we study it in more detail, we will see that this firmware transfers the quote-unquote password hash. And if the quote-unquote hash matches the original one, if it doesn't, it generates an error code. Here you can also see a function called calc hash passive, which is the one we are primarily interested in. If we enter this function, we will see an algorithm where the password is obfuscated and deobfuscated. You will see that it's done using the simplest operations, such as XOR. It's, by the way, a very symmetric algorithm. If you run it in Python, you will be able to actually take from the traffic the hashed passwords and decrypt them, which means that such a hashing algorithm is, shall I say, not secure enough. In fact, in many industrial devices, we should be able to find both attack resistant and not so good, on the other hand, encryption tools relying on not very good encryption primitives. We are discussing here vulnerabilities in other industrial equipment. Why is this the case? PLC is the most important part of ICS, but it's not the totality of the network, right? And PLCs are the intermediary between the physical equipment and the operator's laptops. When network equipment is attacked, connection to PLC will be endangered. The technological process itself will continue to run. However, the features for managing technological process remotely will be undermined, although you will be able to manage it locally. This is something we are going to discuss after a short break. Please stay tuned. At 5 p.m., we shall continue after this very short break. I am going to share with you my own experience where I found a vulnerability in the industrial equipment produced by a very well-known vendor. And as I tried to exploit it, I bricked it. And it was a shame because it cost something like $5,000. And I'll tell you the rest of the story, how I tried to extricate myself from the consequences of this bricking. Please stay tuned. Let's continue at 5 p.m. This is roughly 16 minutes.